Hello, good day everyone, and today we are going to continue again our topic, no, this reinforced concrete design, and we are dealing now with the working stress design, and this would be our part 3. And before we will proceed, no, to our discussion, please don't forget to subscribe, no, to my YouTube channel so that you can be notified, no, for my future lecture videos. Okay, so proceeding now with this topic today. So we have these elastic stresses, no, in which the concrete has experienced now this crack or cracking, and we are dealing also with this working stress design. Okay, so when the bending moment is sufficiently large to cause the tensile stress, no, in the extreme fibers to be greater the modulus of rupture, so it is assumed that all of the concrete on the tensile side of the beam is cracked. Okay, and take note, must be neglected in the flexure calculation. Okay, so you have to remember this one, no, because when we are dealing with this working stress design, you can see that the concrete, no, this concrete on the tensile side of the beam, since this is cracked and this is being neglected, no, in the calculation of flexure. Okay, and on the tensile side of the beam, actually an assumption of a perfect bond, no, is made between the reinforcing bars and the concrete, and the strain in the concrete and in the steel will be equal, no, at equal distances from the neutral axis. And if the strain in the two materials, no, at a particular point are the same, their stresses cannot be the same, no, also, even though their strains are similar, no, or the same at a particular point, but take note that their stress, no, will not be the same. Okay, and you may ask why, no, if they have the same strain but they don't have the same stresses. And if you ask me why, because they have different moduli of elasticity, no. The steel has a different modulus of elasticity, and also for the concrete has a different modulus of elasticity, so that is why their stresses will not be the same, no, even if their strains, no, of these two materials are the same at a particular point. Okay, and because of this, we have this ratio, no, of this steel to the concrete modulus, and we call this one N, no, this modular ratio N, and it is just equal to the modulus of elasticity of the steel over the modulus of elasticity of the concrete. Okay, so in layman's term, we can describe this one, no, if the modular ratio here N of a particular beam is 5, so we can say that the stress, no, in the steel will be 5 times the stress, no, in this concrete at the same distance from the neutral axis. Okay, try to remember that one, no, because this is the essence, no, of this modular ratio N. Okay, so proceeding now, so we have this figure 1, no, in which in this figure the steel bars are here, no, are replaced with an equivalent area of fictitious concrete, and it is denoted, no, by this N times the area of steel, which supposedly can resist tension, and this area is referred to as the transform area. Okay, so take note of this one. This is referred now as the transformed area. And also shown in this figure is the diagram showing the stress variation, no, in the beam, and on the tensile side, no, as we can see it here, a dashed line is shown because the diagram here is discontinuous. Okay, and the concrete is assumed to be cracked, no, and that is why we have now this dashed line, because the concrete is assumed to be cracked and unable to resist tension, no, in this side of the beam. And the value shown here, this Fs over N, opposite the steel. This is the fictitious stress, no? This is a fictitious stress in the concrete if it could carry tension. And the value, though, this value must be multiplied, no, by N to give the stress, no, of the steel, and it is denoted by this F subscript S. Okay, to get this F subscript S, which is now the stress, no, of the steel, we just have to multiply this one, no, with N. Okay, and the first step actually here, no, for this transformed area method is to locate first the neutral axis. We need to locate, no, this neutral axis, and then we are going to assume, no, to be located at a distance x, no, from the compression surface of the beam. Okay, so we may assume it here, no, from the compression surface here, so we can assume this one as our x, no, distance, and the resulting equation here is actually a quadratic equation, and this can be solved by either, no, using the quadratic formula or by completing the squares. And the moment of inertia of this transformed section here and the stresses are computed, no, using the Fletcher formula. Okay, so try to remember this one if we are dealing with this working stress design and the concrete has experienced, no, this crack or cracking. So we need to use this transform method, no, in solving this kind of problem. Okay, so now we are going to this board problem number 1, no, considering this working stress design, and we are going to calculate the bending stresses in the beam shown given this FC prime, okay, equal to 20.7 megapascal, and our modular N, no, is equal to 9, and the moment M is just simply equal to 95 kilonewton meter. And we have here, no, in this figure 1, we have this depth of 510 mm, the width of the beam of 300 mm, and we have these 3 pieces of 10 mm diameter bars, and we are going now to calculate the bending stresses given this FC prime and this moment M. Okay, so proceeding now as our solution for this. So as being discussed, we need to assume distance x, no, from this neutral axis. So we need to establish first and locate this neutral axis, and we need this transformed area method in which this is our x distance, and probably the distance, no, from this neutral axis to this area of steel, no, this transformed section for this N area of steel is just 510 minus your x. Okay, and we are going to locate the neutral axis, this NA. So assuming this would be now our neutral axis with using this transformed section, so we are going to determine now the location of our neutral axis now with respect now to the top of this beam, okay, at a distance x, using the moment area of this section here equal now to the moment area of this section, no, below this neutral axis. So we can have now this 0.3 referring now to this 300 mm, no, so in meter, our unit here is in meter, so 0.3 times your x, no, times this x over 2. Okay, the moment area of this section equal now to the moment area of this section below the neutral axis. So in this case, for the moment area of this here below the neutral axis, we have now this N times the area of steel, And we have now this 510 minus x, no? So we are using the unit of meter, so that is why we have 0.51 minus x here. Okay? Okay, so I hope you do not be confused, no, with this moment area here, because if you are going to consider this part here, our area is 300 times x, okay, and this is 0.3 times x, and this arm here, since we are using a moment area, why is it that this is x over 2? Because as you can see it here, we need to locate, no, the centroid of this one, which is probably here. So the distance from here until this neutral axis, no, so probably its distance is just equal now to x over 2. Okay, this is x over 2. So that is why we are using, no, this x over 2, because this is the centroid, no, the centroid of this section here, and its distance to the neutral axis is x over 2. Okay, so that is why it is x over 2. And for the case of this section here below the neutral axis, so its area is this n times the area of steel. So this is already an area, okay, and its arm is just equal now to this 510 minus x. Okay, so its distance, no, from here, no, to the neutral axis is already known, or equal to this 510 minus x. Okay, so that is why it is 0.51 minus x, no. This is its moment arm actually for this section here, n times area of steel, but the moment arm for this section here of this 300 times x is just this x over 2. Okay, so proceeding now, so we can get, no, the value of our x, no, actually, but we need to calculate first the area of steel. Okay, so based on the problem, we have actually three pieces of this 10 mm diameter bar. So first, we need to determine the area of this 10 mm diameter bar. Afterwards, we are going to multiply the number of pieces of 3. And then after that one, since this is n times area of steel, so we have to multiply with 9 because our n is given in the problem, no, which is 9. Okay, so you can get the value of your n times area of your steel equal now to this 0.002121 square meter. Okay, so after that, we are going to substitute this value here, no, so we have here, and then using your calculator, you can actually get the value of your x, which is just simply equal to about 78 millimeter. Okay, so x is just equal now to 78 mm. Okay, so after this, we already established, no, the neutral axis, no, at a distance x from this top fiber here, and then we are going to calculate the moment of inertia. Take note, we are going to calculate the moment of inertia considering the neutral axis. Okay, considering the neutral axis. So now I will present to you, no, what's the difference of using the neutral axis and this centroidal axis. Okay, so we have here this formula, no, the gross moment of inertia is just equal now to this I subscript gx, no, plus your a times d squared, okay, equal now to 1 over 12 bh cubed plus this ad squared. So this is used for, take note of this one, this is used for centroidal axis only. Okay, if you are going to consider centroidal axis, you need to use this formula for the moment of inertia. But how about if you are going only to consider the neutral axis. So we need to use this formula here. Okay, your gross moment of inertia is just equal now to 1 over 3 bx cubed plus ad squared. So remember this one. Okay, try to remember this one. If you are going to use the neutral axis, use this formula for the gross moment of inertia. But if you are using the centroidal axis, you will use this formula for the gross moment of inertia. But now we are using the neutral axis for this working stress design using the transform section. So we need to use this one also in our calculation here. Okay, since we are using the neutral axis, so use this formula. So proceeding now. So our gross moment of inertia is just equal now to 1/3 bh cubed plus your area here, take note, area is referring now to this area, to this area. Okay, so this area is just equal now to your n times the area of your steel, referring to this one. Okay, and this 1/3 of your bh cube is referring now to the area of this side, above this neutral axis. So substituting now, so we have this 1/3 of your 0.3 times this x, which is 0.078 in meter, and then raised to the cube, plus this portion here, in our transform section, which is n times area of steel, which is equal now to 0.00221 times our distance here. Okay, d, this is now the distance, to the neutral axis. So in this case, 0.51 minus x, and this is squared, so that is why it is squared. Okay, so after that, we are going to determine now the value, of our gross moment of inertia, which is then equal now to 0.0004433 m to the fourth. Okay, so proceeding now, so we are going to calculate the bending stress, and then we are going to consider the bending stress for the concrete side, and also for the bending stress for the steel side. So for the concrete, we have this my over I, and then this is just equal now to m times x over the gross moment of inertia, and we are using x because we are considering the concrete, which is referring to this section, and its distance from the neutral axis is x, so that is why we are using now this x here. Okay, so substituting now the values here, we have this 95 kilonewton meter, which is given in the problem for this moment, and this 0.078 meter here over this gross moment of inertia. Okay, so we can have this bending stress for concrete equal now to 16.72 megapascal. Okay, so now we are going to proceed to this steel. Okay, take note, the F of your steel over n is just equal now to my over this gross moment of inertia, and here, since we are referring now to this transform section for this part here for the steel, so its distance from this to the neutral axis is this 0.51 minus x, so that is why we are using the value of our y, which is equal now to this 0.51 minus x. But maybe you are wondering, why is it that this is F steel over N? So to clarify this one, actually, its original formula is just simply Fs, Fs is just equal now to your my over your gross moment of inertia. Okay, But as you can see, in our previous slide here for the stress diagram here, okay, after this one, so we have this dash line, no? So this is denoted by Fs over N, and this is our Fc, and this is now our stress, no? For the stress diagram, okay? So this means that we have this dash line here as previously discussed because the section, no, experiences this cracking, and that is why, as what I mentioned, no, that in the flexure calculation the concrete is excluded, no, in the flexure calculation, and that is why we are only considering this stress, no, in the steel, which is Fs over N. Okay, so that is why we are using here, no, this Fs. Our Fs over N is just equal now to the F of your steel over N. Okay, and in which this one is just equal to this one here. Okay, so we are using Fs over N. This is now the stress, no, on our side here, on the tension side of the steel, and the concrete is being excluded, no, in the calculation as being discussed. That is why we are using here this Fs over N because of this stress diagram here, no. So do not be confused. Why is it that we are using this one here, no? Originally it is Fs, no. Fs equals to my over this gross moment of inertia. But because of this reason, no, that the concrete experiences a crack, that is why it is being excluded, no, in the flexure calculation. And based on the stress diagram, it is Fs over N. So our Fs is just simply replaced by this, no, by this Fs of your steel over the N, which is just equal to this Fs, referring now to the F of your steel over N. Okay, so proceeding now, we are going to just substitute, no, the values here, and we can calculate, no, our value of your, take note, no, this one here, N is 9, so we cross multiply, so that is why we have 9 here times your moment of 95 times your difference of 0.51 minus x, no, which is 432 mm or 0.432 meter over your gross moment of inertia. And actually this is our F of your steel. Okay, this is the F of your steel, no. And calculating, we have arrived now to this value of your F of your steel equal now to 833.21 megapascal. Okay, so now we are done with the bending stresses, now for the concrete and steel. So we proceed to the calculation of the modulus of rupture to verify if the concrete section or the beam section is really experiencing crack or cracking. So now we are going to calculate, no, the modulus of rupture Fr using the formula of 0.7 times lambda, which is equal to 1 times square root of Fc prime, which is 20.7, and this is just equal to 1.92 megapascal. So from there, we can say that your F of your concrete and your steel is greater than the modulus of rupture. So this one confirms and verifies that your beam section really experiencing cracking. Okay, because their values of this F of the concrete and steel are greater than the modulus of rupture. So therefore, we have now this conclusion, no? The F concrete and F steel is greater than if or rather those the beam has crack. Okay. So I hope this is very clear, no, to everyone regarding this working stress design, in which we consider, no, that the concrete or beam experiencing this crack or cracking. And we have now this as a note, no, for you here. So as you can see, when the bending moment is sufficiently large to cause the tensile stress in the extreme fibers to be greater the modulus of rupture. So this bending moment is sufficiently large, no, will can be manifested, no, through the value of your bending stress, no, of your concrete and of your steel, because this bending stress of your concrete and steel is directly proportional to your moment. So that is why when it says that the bending moment, no, it is also synonymous of saying that when the bending stress, no, of your concrete or steel is sufficiently large to cause the tensile stress, no, tensile stress meaning at below this neutral axis, no, and in this part at the bottom, no, or at the bottom part of your section. So to be greater the modulus of rupture, so it is assumed that all of the concrete on the tensile side of the beam is cracked. So that is why it is being represented by that dashed line, no, in the stress diagram, and must be neglected in the flexure calculation. Why is it that it is neglected? Because the main reason that it is being neglected is we are only using this n times the area of your steel, no, as you can see, no, we are no longer considering concrete, no, but below this neutral axis we are only considering your modular ratio n times the area of your steel. So you can see you cannot see concrete here anymore, no. That is why must be neglected in the flexure calculation, because we are only considering this modular ratio n times the area of your steel. Okay, so that would be it, no, for this day. And again, no, I hope you have learned something, and you have learned more and more every time that you're watching this lecture video of mine, no, with regards to the subject reinforced concrete design. And thank you very much, no, everyone, for your time, for listening, and for watching, and for subscribing. And for our next topic, we are going to discuss another CE board exam problem for this working stress design. Okay, so for my references, these are my references. And again, thank you very much for subscribing, for watching and listening, and see you again, no, on my next lecture video. And God bless us all, and keep safe, everyone.